So last time we talked about a bunch of things. We talked about the functional API for building DAGs of layers. We talked about features that are specific to the functional API, things like static input compatibility checks across layers every time you call a layer, whole model saving, model plotting, and visualization. We talked about how masking works in the functional API, in particular how masks are propagated. So for instance, in this example, the embedding layer is going to be generating a mask here because you passed this argument mask 0 equals true. And this mask is going to be passed to every subsequent layer, and in particular to layers that consume the mask, like this LSTM layer here. However, in this LSTM layer, because it's a sequence reduction layer, it's not going to be returning all the sequences, but only the last output. This is going to destroy the mask, and so this layer is not going to see a mask anymore. So it's really a way to handle masking that works basically magically. Masking is pretty advanced, so most people who need it are not actually going to understand very well how it works. And the idea is to enable them to benefit from masking by just doing like, hey, I have this embedding layer, I want the zeros to mean this is masked, and then everything in their network is going to magically know about this, as long as they're using built-in layers. If you're an implementer of layers, you actually need to understand how it works. Particularly, you need to understand what you should be doing if you're writing a layer that consumes a mask, like an LSTM layer, for instance. It's very simple. You just make sure you have this mask argument in the signature and expect a struct of tensors that's going to match the struct of your inputs. So typically, it's going to be a single tensor. And the single tensor is going to be a Boolean tensor, where you have one mask entry per time step per sample. So it's typically a 2D Boolean tensor. If you have a layer that can safely pass through a mask, for instance, a dense layer, or in general, any layer that does not affect the time dimension of its inputs, you can just enable your layer to pass through its mask by saying it supports masking. It is opt-in because a lot of the time layers might be affecting the time dimension of the inputs, in which case the meaning of the mask would be changed. And if you do have a layer that changes the time dimension, or otherwise a layer that creates a mask from input values, it's going to need to implement this compute mask method that is going to receive the mask, receive the inputs. If, for instance, you have an embedding layer, it's going to be doing this, not equal input 0. So it's going to be using the input values to generate a Boolean mask. If you have a concatenate layer, for instance, it's not going to be looking at the input values, but it needs to look at the masks, the two masks being passed, and concatenate them. And if one of the masks is none, for instance, it's going to have to generate a mask of ones. Okay, so that's the very detailed, yeah.
So just maybe a little bit more detail about masking.
Yeah.
So if you say supports masking is true, but you're like in the lower left-hand corner,
yeah.
Is that just using some default version of?
Yes, and the default is pass-through. So it is, if you say this, this enables your layer to use a default implementation of compute mask, which just says return mask. So it gets the inputs and the mask and just returns the mask unchanged.
Okay, and
so that assumes that the mask is like the first dimension, second dimension gets masked?
The first dimension gets masked if 0 is a batch dimension.
So, and then where does this mask argument come from? Like if I look at the previous slide, like it's not clear to me at all how this mask is being propagated.
So it is generated by the embedding layer from the values of the integer inputs.
Right. So embedding layer has a compute mask function.
Yeah, which is exactly this one actually.
It returns a mask.
Yes.
For some, and somehow the infrastructure knows to call, because you said you enabled masking, it knows to call the compute mask thing.
Yes.
But the mask gets generated, but I don't know where it gets put.
Where it gets put. So that's actually something we're going to see in the next slide, which is a deep dive into what happens when you're in the functional API. You have some inputs you've created with Keras.input, and now you're calling a layer on that. Well, the first thing we do is check whether all the inputs are actually symbolic inputs, like coming from this input call, because there's two ways you could use a layer. You could call it on actual value tensors, unlike eager tensors, in which case you're just going to run the layer like a function and return the outputs. Or you could call it symbolically, which is what happens in the functional API. Then you run pretty extensive checks about the shape and d-type of your inputs to raise helpful error messages in case of a mistake made by the user. Then you check if the layer is built. The layer being built means its weights are already created. If the layer was not built, you're going to use the shape of the inputs to build the layer. So you call the build method. And after you've done that, you actually do a second round of input compatibility checks, because the input spec of the layer is quite likely to have changed during the build process. For instance, if you have a dense layer, when you instantiate it before it knows its input shape, its input spec is just the fact that its inputs should have rank at least 2. But after you've built the layer, then you have an additional restriction, which is that now the last dimension of the inputs should have a specific value. Then the next step is you're going to check if you are in this case, if this layer expects a mask argument. And if it does, you're going to be fetching the masks generated by the parent layer via this compute mask method. And
so where does that come from? I mean, like somehow there's a secret communication channel.
Yes, which is a bit of metadata set on the tensor itself. There's an underscore Keras mask property, which is the mask information. So it is the least error prone to collocate the mask information with the tensor with which that it refers to.
So if you were to do something like, I don't know, like a relu or something that's not a layer.
Yes.
So you get a tensor that doesn't have a Keras mask argument, but then you say, I guess you're also going to put it into a lambda layer.
So what happens when you call ops that are not layers is that they get retroactively cast into layers, essentially. Like we construct objects that are layers that they are going to be internally calling these ops. But these automatic layers, in the general case, do not support masking. So if you do this, you are destroying the mask, and you're going to be passing your mask to a layer that does not support it, which is an error. So it's not going to. It's not a silent failure. It's an error. If you pass a mask to a layer, which is one of these automatic layers in this case, that does not support masking, it's going to yell at you.
So, but wait a minute. I feel like lots of layers are going to be like sort of trivial pass-throughs. Like if there's a mask, we want to pass it through. But if there's not a mask, that's fine.
Yeah, so it has to be opt-in again, because any change to the time dimension of the inputs would need smarter mask computation. And we cannot just always implicitly pass through the mask, because you don't actually know what the layer is doing.
If you could really change to implicitly pass through the mask as the shape of the outputs, the shape of the input.
But what about something like a cube sum?
That has the same mask. That should actually respect the mask.
I think it's a reasonable default behavior. It's not going to work all the time, actually. You can think of adversarial counterexamples, but they're not like common counterexamples. But yeah, so currently, masking with the functional API is something that's only useful for built-in layers very much. So it's not really an issue we ran into before. I like the fact that currently it's opt-in because this actually saves us from precisely people generating a mask in some embedding layer and then passing it to a custom layer or an automatically generated layer that does not support it. And that would that could potentially do things you don't expect, right? So it's better to.
And is the mask supported in eager execution?
Yes, it is. So in eager execution, essentially what happens is that the call method, which is programmatically generated for one of these functional API models, is basically going to call both underscore the call method of a layer and its compute mask method, and gonna call the next layer with these arguments. So essentially very much what you would be doing if you were to use masking using subclassing, which is basically you call your layer, you get the outputs, your sublayer. I don't have a good example here. So you call a layer, get its outputs, then you generate the mask using compute mask explicitly. And for the next layer, you're going to be explicitly passing this mask argument.
And is it just keyword arg mask equals?
Yes, that's right.
So like all these layers take implicit keyword arg mask equals. So if I feel like the mask is getting dropped, I can always fix it by passing an explicit one?
Yes, that's correct. You can pass arbitrary Boolean tensors, well, 2D Boolean tensors as the mask argument. So in general, if you're doing subclassing, nothing is implicit, and you have freedom to do whatever you want, basically.
Question about masking and the loss. Like, if you have a particular loss that takes like 3D tensor or like trying to filter out the padding data, does the mask get propagated to the loss?
Yes, that's right. So in this example, for instance, our sequence reduction at a CM layer would have been destroying the mask. But if you were to remove these last two layers and just say this LSTM layer that returns sequences is your last layer, and then you apply a loss function that is sequence aware, then yes, the model during fit is going to generate a sample weight argument for the loss, which will incorporate the mask, meaning that any time step that is masked is going to receive a 2D sample weight of 0. So yes, so if you have something like, for instance, per time step classification, and you have time steps that are padded or masked, they will be completely ignored by the loss. So resuming, what happens when you call a layer on symbolic inputs? After you've retrieved the mask, you've run the input compatibility checks, you've built the layer optionally, you're going to build a graph for the operations done by this layer. And there are very much two possibilities. Either the layer can be converted to a graph, which is the case 99% of the time. In that case, we're going to use autograph to generate an autographed version of the call method. This is useful in case the layer implementer is using Python control flow, like if and for loops and so on. And then you're going to be calling this autographed version of call on your symbolic inputs. And in this call, you're going to be incorporating the mask argument, if it's present, and the training argument, if applicable. If the user has not passed an explicit training Boolean argument in this layer call, then it will default to the Keras learning phase tensor, which is a global symbolic tensor that we set its value when you call fit or evaluate. In the rare case when the layer is declared to be dynamic, meaning that it cannot be converted to a graph, this is the case, for instance, for a tree LSTM layer and so on. So it's very niche cases. In that case, you will expect the layer implementer to have implemented static shape inference. So compute output shape method that takes input shapes and return output shapes for this layer. And you're going to use this static shape inference method to generate new symbolic tensors with the correct shape and d-type. And you're going to be returning that. So once you've created the subgraph corresponding to this layer, you're going to create a node object, which is, again, a node in the graph of layer object that the functional API builds. You're going to set metadata on the outputs corresponding to the node. So essentially, the layer call that created these outputs, and also mask metadata. So that's it. It's actually a lot of features in one. So we talked about dynamic layers, layers that can be graphed and layers that cannot be graphed. So last week, we saw an example of a very simple batch normalization layer implemented with subclassing. And in the call method, you had this if training conditional. And in training, you're just going to compute the mean and variance of the current batch. You're going to normalize the current batch with its own statistics. And you're going to be updating the moving variance and moving mean for your layer. In inference mode, however, you're going to be normalizing the current batch with the moving mean and moving variance. So there's actually a small subtlety with this layer, which makes it unfortunately ungraphable, which is basically doing assignments of variables, so updates, in a branch of a conditional. This would be relatively easy to avoid.
Why is that uncomfortable?
So it's a problem because each branch in TensorFlow control flow v2 is going to be run in a different fun graph. And so
That's the control flow v2 is perfectly fine with this.
It's because you only have an assign in one branch. If you had a corresponding assign in another.
No,
You can have a sign on. Like,
there might be a bug, but it's a bug if
Yeah.
this doesn't work.
so anyway, yeah, let's say it's a bug.
If,
So
if you replace the assign with like self.add update, then you have a problem because you can be leaking a tensor from a control flow branch. But assign is safe. It's self.update.
So last time I tried it, this wasn't working. If you moved the assign outside of the if statement, it would be working. So, but anyway, let's say you have a tree LSTM layer. You cannot graph it. What do? You pass in the constructor, when you call super, you pass dynamic equals true. This tells the framework that this layer cannot be graphed. And when used in the functional API, it's never going to be used to build a graph. And when you call fit or evaluate, we're always going to run everything eagerly, even if you don't set explicitly run eagerly equals true. One thing to keep in mind if you have dynamic layers is that if you want to use them in the functional API, you will have to implement a compute output shape method to tell the framework how to do static shape inference with this layer. If we cannot do static shape inference, you cannot use your layer in the functional API, unfortunately. So if you try to use your layer in a symbolic way, it's going to get at you, telling you to implement static shape inference. So that's it. And yeah, and so when you call fit, it's automatically going to be run eagerly. So of course, if you're not using the functional API and you're not using fit, then this dynamic argument is irrelevant to you. So let's talk a little bit about training and inference. So as we said last week, so compile is about basically configuring the training procedure. So it's all about building essentially an execution function, an execution graph. Meanwhile, fit is about running this execution function with new data over a data set. So what happens when you call compile? Of course, checking the values of the arguments passed by the user, because it's always important to do sanity checks and raise good error messages if the user has made a mistake. Then we are going to look at the loss argument. We're going to map it to the different outputs. Not all outputs might be passed a loss. you're going to do the same for metrics as well. You're going to compute the total loss, which is the sum of the per output losses and any loss that's being added during the forward pass. You're going to retrieve the trainable weights of the model and use the total loss and trainable weights and the optimizer that you passed to compute gradients. Then you're going to prepare the inputs, outputs, and updates for different execution functions, which are basically fun graphs. So you have 3 different execution functions. You have the train function, which takes input data and input targets, and it's gonna run the backprop updates and the forward pass updates, and it's gonna return the loss and metric values. Then you have the eval function, which does the same except without running any updates. So it's not doing backprop in particular. It just takes input data, targets, and it computes loss and metrics. No updates. And finally, you have the predict function, which is like eval except with different outputs. So it's not gonna running any updates. It's taking the input data and targets, and it's going to be returning the output of the model. It's not going to be returning the loss or the metrics. The way these execution functions are implemented in TensorFlow v2 is as fun graphs. When you're calling a layer symbolically, so in the functional API, that happens in a global Keras graph. And when you're creating an execution function, you're going to be creating a new scratch fun graph, and you're going to be doing a copy of the relevant subgraph from the global Keras graph to your new graph. And then that's this copy that you're going to be running. So that's, if you're creating different models, the execution functions are all separate, living in different fun graphs.
So here we have, so it seems like there's some weird things where, like, for example, an optimizer is not used for eval and predict. Is it, what happens if can you just not set an optimizer?
So yes, you can just not do compile and then do predict. That works because you don't need the compile information in order to run predict. However, you do need to compile your model if you want to run eval, because eval needs to compute loss and metrics, which are passed in compile.
Well, I guess, but what if you don't have, like you're only doing eval, do you need an optimizer?
Technically, yes. I think it's possible you could pass none as the optimizer. That would work. I don't recall. I think it's required. It's required. Yeah, so in that case, you can just pass the default optimizer, like the string SGD. It's going to work fine.
Okay, but I guess then it's going to create a bunch of graphs that I'm never going to use. But.
So the execution functions are actually created lazily. So they're not actually created in compile. It's a good mental model to have to think they're created in compile if you want to think about it. But actually, for instance, when you call fit that the train function is going to be created. It's when you call evaluate that the eval function is going to be created, and so on. So you're only going to be, if you just instantiate your model, compile it, and call evaluate, you're not going to be creating any graph ops related to your optimizer, because you're only creating the eval function, which does not need the optimizer.
I thought you can do model optimizer equal to none specifically.
But it's kind of an use case. So anyway, you can definitely instantiate a model and call predict without having called compile, and that totally works.
Because are any of the arguments, so none of the arguments from compile are used for predict?
Are useful for predict, that's right.
Okay.
Because predict is just input to output mapping.
But aren't outputs also prepared in compile? So it just prepares them.
And how do you feel like when should people consider using model to predict versus just calling the model and then by input?
So model.predict is gonna iterate over the data you passed in many batches and gonna return NumPy arrays. Meanwhile, calling the model on an eager tensor is the same as calling a layer, so it returns directly this value. If you have a single batch, there is no difference.
There's one, in a lot of cases, if you call model on something, it goes through the eager path, whereas if you call predict, it goes through this function path. And so if you're sensitive essentially to the graph execution versus eager time, predict can be much faster.
Yeah. So, and if you have a, yeah. But in terms of end output, if you have a single batch, there's no difference. But the big difference is that to predict, you could pass, for instance, a data set, right? Which you cannot pass in call. Yeah. So what happens now when you call fit? There's pretty extensive checking of the user-provided data as usual, checking that the correct data is being passed, that it has the correct shapes or rank, and so on. So optionally, we can set aside the validation split. That's only true if the input data is NumPy data or eager tensors. That's not possible if you pass a data set or a Python generator. Then we prepare the callbacks. So importantly, everything that happens dynamically during training, apart from executing the graph functions, is structured as a callback. In particular, the logging that we do internally and the display that we do of the progress bar, these are all callbacks. And if the user also wants to do some action dynamically during training, they have to implement a callback.
How often are callbacks called?
So they're called at different points during training. So a callback implements the methods onTrain begin and onTrain end, which are called at the very beginning, before training and after training is over. And then for each epoch, you have a method onEpoch begin and onEpoch end, so called before the start of an epoch and after the epoch is finished. And finally, there's batch level methods. There's onBatch begin and onBatch end.
Is the infrastructure able to know whether a particular callback is implemented on batch begin and on batch end to avoid maybe a per batch overhead?
So if the method is not implemented, there's virtually no overhead to calling it. And we need to call it anyway for things like the history aggregator and so on.
For what?
The logging callbacks, basically.
I guess like in cases where we're trying to put the whole training loop on device, for example, or we're trying to do, say, remote execution, where per batch execution might be.
Yeah. So one thing we've considered, this is a topic that has come before with TPUs and so on. One thing we've considered is having a global, an argument in fit or something that specifies how often batch level callbacks are going to be called. Like for instance, every 30 batches and so on.
So the batch, so what if a batch argument is only called every 30 batches or something like that, is that going to, I mean, how does it work? Are callbacks expecting to see something every batch? Are they going to still work if they're called every 30 batches?
Typically, that's still going to work. The way it's going to work is that from the perspective of your callback, it's going to be the same as if your batches were 30 times bigger.
So the batch, the callback will be called the concatenation of all batches?
Does it get the output?
Well, this is a speculative API, right? We don't have this implemented, but this is one way where we've considered handling the fact that you're probably going to be wanting at some point to do processing of multiple batches at once on device with no contact with the host.
So I guess could you just tell us what on batch begin arguments are? Like what sort of information is passed to those?
Right. So it receives a log dictionary and it receives the index of the batch as well. The log dictionary contains the current value of the total loss and the metrics. So
that the loss from the last batch or the loss
so that's the loss from the last batch, and these are the metrics, the moving value of the metrics.
But even if we change the callbacks, I think, and as long as the loop itself is in Python, it doesn't really help, right? Even if you're not calling a callback, as long as the loop is still in Python, it doesn't
We
really.
could try to turn the loop into
Yeah, so I think that would be
but I
required
think
as well.
now the expectation is that the callbacks are operating on NumPy arrays, not tensors. And I think we need to change the API so that the callbacks would operate on TF tensors, so that would work.
I mean, I think in a perfect world, we would use a mixture of Python and PyFunction to essentially only run in Python the parts that we want while still keeping the outer part. But I mean, we're not there yet.
And since callbacks are passed in as list, can I rely on the sequence of how they're passed? Is it the sequence how they're going to be
Yeah,
executed?
so the sequence in which they're called matches the order in which they're passed in the callbacks list that you pass to fit, meaning that it is possible for one of your callbacks to add some values to the log dictionary. It's the same log dictionary that's going to be seen by the callbacks after that. So it's possible to do cascading processing like this.
And the default callback, like the progress bar and stuff, are called at the end?
The progress bar and logging stuff is called at the very end, meaning that if you add stuff to the log dictionary, it's going to be displayed. But the very first callback that's passed is actually the callback that starts populating the logs.
There's also a slight bit of nuance in that the model itself is set as an attribute on callbacks. And so any attempt to essentially optimize this or put this in like a TF function scope would have to be aware of the fact that it's a legitimate use case for a callback to start accessing arbitrary parts of the model.
Right. I guess my question is just more about running callbacks less frequently, not about trying to run them inside a function.
Okay, so our last topic is losses and metrics. The losses are very simple. So they're just subclasses of this loss base class. They just have to implement one method, which is call, just like layers. The signature is a bit different. The signature is always white true, white pred. Optionally, you can also have a sample weights. And you just return a loss. So importantly, as a convention, the loss you return should be one loss value per sample. So here, for instance, we're reducing on the last axis, but we're not returning a scalar. Metrics are a bit more involved. There's 3 different methods you should be implementing in your metrics. You have this update state method, which is very similar to the call method for losses. So white true, white pred, sample weight in the signature. And the difference is that you're not returning a value, you're just updating the internal state of your metric. So in this case, your internal state is just this one scalar weight called true positives. So here you're just adding to this value. Then the second method you have to implement is result, which, as the name indicates, just returns the current value for this metric. And finally, you need a method to reinitialize the state of your metric. And what happens, for instance, when you call fit, is that at every batch, we're going to be updating the state of the metric, so calling this update state method. When we want to report a value, which, well, typically it's also after every batch, we call this result method. And at the end of an epoch, we want to reset the metric, so we call reset states. And the way you specify metrics in the compile API is basically you just have this metrics argument in compile, which takes a list of these metric instances. So if you have metrics with signatures or like requirements that do not match this API, that you can update the state based on white true, white pred, and some sample weights, for instance. One thing you can do is write a layer that will, inside its call method, that will call cell.addMetric with a scalar tensor. And that enables you, so there's two arguments you need to pass. You need to pass a name, because that's what's going to be reported with the progress bar and your logs and so on. And an aggregation argument, which tells the framework how so this, you can assume that this is basically called for every batch. So how does these different values for every batch get aggregated into a single scalar, right? And then in the functional API, you can use this layer like this. You insert it at some point, just returns the same as its input tensors, which you can keep using. And when you do that, you get a model with a forward pass that's going to be calling this add metric at every batch.
Are there any standard predefined versions of metric logging layers?
No. But it looks just like this. So there's nothing special you have to do apart from implementing call with an add metric in it.
How does that work in eager execution?
In eager execution, this is literally call at every batch.
So you add a new metric in every batch? Or is two people create metrics with different metrics with the same name? Can you catch that?
We keep track of the metric with the name and just call the same metric again. So
I see. So if you have two layers that call that metric and they both use the same name, then you're going to have a collision.
We'll raise an error in that case.
Oh, so you just detected the layer, but if the layer adds two metrics the same name, you assume that's intentional.
So essentially, in one forward pass, you cannot have the same name twice. But across different forward passes, so across different calls of your method, of your model, you're going to be aggregating the metrics based on the name.
So there's some state that gets reset.
Yes, that's right.
So is this similar to the thing where layers know if they're being called by another layer?
Yes, it's very similar. It's basically a call context, and at the end of the call context, you reset the state. So you reset the losses that were created during the forward pass, and you reset the state of this metric aggregation thing. Right. So, but what if this is not actually enough for you, because you want a metric that not only sees the input of your model, but also the targets, which is actually relatively common. One thing you could use, so of course, if you're just doing a model subclassing or writing your own custom training loops, you have no restrictions whatsoever, so it's not relevant to you. But what if you really want to use fit with these very arbitrary metrics? Well, one thing you can do is the endpoint layer pattern. So how does it work? It's basically a layer that in the functional API you would put at the very end of your model, so it computes the predictions, right? And it's gonna take as input whatever you want. In our case, it's gonna take the targets of the models and logits generated by this dense layer here, and the targets are an input, right, created here. And then what is it gonna do with inputs and targets? It's gonna compute a loss value. So it returns a scalar in this case, because we call it with __ call, which is different from the plain call method. So it's automatically reduced in this case. You can add whatever metrics you want. Note that if you add a training argument here, you could be logging different metrics in training and inference. And finally, you return what you would want the predict method to return, so a softmax in this case.
Well, it seems to me like you can't use this with inference at all.
So in inference, you will be using the same layer, for instance, but what you can do, you will have to rewire your model, because you're not going to have these targets inputs. But you can use the same layer. The only thing you need to be mindful of is that you should do a conditional check on the inputs that were passed to see if there is a targets key in there or not, and if there is, or you could rely on the training argument, also works.
So you're saying that, like, if I create this model like you show it in there, and then I call model.predict on it.
So if you just reuse this is a model that's only for training. If you reuse it for predict, you're going to have to pass some value, some dummy value for the targets. So if you want to not have to pass dummy value for targets, you need to redefine a new model that's going to be using the same layers. The only difference is that it's not going to instantiate this target input object, and it's not going to be passing the targets to the logistic endpoints. And your logistic endpoint is going to it's not going to attempt to access the target's key. Yeah, so this is so when you instantiate this model like that, you say it starts from inputs and targets, it returns predictions, and when you fit it with a dictionary or data set that returns a dictionary, and you include the target's data in that dictionary, so like this, right? And when you compile it, you are not going to specify any loss in compile because the loss is added entirely inside that endpoint layer. So you just specify the optimizer.
So is the name in, like, when you define the inputs for the inputs and the input for targets, is the name in there supposed to match the key in the dictionary?
Yes. So when you call this layer, you're passing this dict. This dict is like
not the logistic endpoint. I mean the input layer. How does model.fit know to pass like inputs to inputs and targets to targets instead of the other way around?
So it's a bit confusing because we have a naming collision here, but in your data dictionary, the keys are supposed to match the names that you gave to your inputs. Okay. So here you create an inputs that's named inputs, here you create targets that's named targets, and this is what these keys here are referring to. So yeah, to deconfuse, we could have chosen another choice of name for the inputs to the heuristic endpoint layer.
Question.
Yeah.
Is it possible, like in here, you're declaring the loss and add the loss on the layer level? Is it possible to just declare the loss and then use the loss at metric, and then don't do softmax, and then just return the y true and y predict, just pass this through? So that, like, later on, like, you still can declare a loss on the model level?
So I don't think there's a way to tell Keras that one of these outputs of the model is the labels.
Yeah, so if you want to pass your loss in compile, it means that the targets are going to be passed separately in fit. And it means that your loss should match the signature y true, y price, sample weight. So if you have anything that's outside of this template, you actually do need to use add loss and to use this pattern, which is very general. Like, there's literally nothing you cannot implement with this pattern. And again, the purpose of this pattern is to make it possible to use fit, a plain call to fit, with complicated loss and metric setups. Yeah. So what if you have a use case that's like even more complicated and you still want to use fit? Well, the answer is don't, because fit is really this built-in thing that's not meant for every use case. It's meant for common use cases. If you need more flexibility than what's provided by this endpoint pattern, for instance, you should rewrite your own loops, which is not difficult at all. So that's it for the overview of Keras internals, and I see we actually spent like 45 minutes on this. So it's nice that we had 2 full sessions. Yeah, so thank you very much for listening and for the interesting questions.
Thank you, this was very informative.
So could you highlight, you talked a lot about how everything works with functional models.
Yeah.
Could you highlight just any differences about things that with subclass models or sequential models or anything like that? Because I know for sequential models, for example,
so
build happens at a different point than...
Yes. So I covered writing things from scratch towards the beginning. But basically, there is very, very little to know about it because everything is explicit and you are in charge of doing everything. So because of that, there's not much happening under the hood. There's virtually no hood. But yeah, basically the first 10 slides in this presentation cover pretty much everything you need to know.
I guess I felt like it covered the difference in the API perspective, but is there anything like like things that we might expect to be true about models, like that they're already built by the time they get to fit or something like that, that may not always be true for like a sequential model or something.
So if you're using a subclass model and you're using fit, one thing to keep in mind actually is that when you call fit, the model is not built. So the framework is going to be looking at the input data you passed to fit and going to assume that you made no mistake and that the model expects exactly the structure of input data. And it's going to use that to build the model.
Okay, so it calls build.
So build happens in fit for subclass models.
So that's only if you're using a subclass model plus fit. If you're using a subclass model plus a custom training loop like this one, for instance, there's really nothing special you need to know.
Is the role of train and batch, test and batch, and evaluate and batch relating to the last slide where you say if you do something complicated, write your own loops? Is that why they exist?
Yes. So these are ways to run the train, eval, or predict execution functions for a single batch. And they are useful if you want to customize your training loop, but you don't actually need the level of flexibility that's provided by the gradient tape, for instance. Essentially, you're going to be using that if you're doing GANs, for instance, or if you're doing reinforcement learning. Manually computing the gradients with the gradient tape and so on is mostly useful if either you want to understand every step of what you're doing and not delegate anything to the framework, or if you need to do some manipulation on the gradients themselves. Like some form of gradient normalization that's not covered by the optimizer API, or you want maybe to actually have your gradients be generated by a different model, like virtual gradients. Yeah, this type of advanced use cases involving manipulating the gradients.
Could you go back to the slide where you show the subclass model?
Which one? This subclass model? Let's see. This one?
Sure. So this doesn't actually define build?
So you don't need to, because build would only be to create variables for this model that need to know about the shape of the inputs. If you don't need to know about the shape of the inputs, you can just create them in the constructor. And in this case, this model has no variables of its own. The only variables of this model come from the underlying layers. And when you call the layer for the first time, which is going to happen in fit, you're going to be calling this call method, which in turn is going to be calling the underlying layers. And that's when they're called that internally, they're going to be calling their build method.
I had this impression that Igor and I came up with this case where build was non-trivial even for a subclass model.
I think you're referring to I think there's a place where you call that model with default inputs if those inputs are of such type that can have default values, like a dummy call under build graph.
Yeah, so that's specifically when you call fit on a subclass model that has never been built before. In that case, the framework is going to make some assumptions, some inference based on the data you pass to fit. If you want to avoid that, you can either explicitly implement a build method and call it, or you could call your MLP instance here on one eager tensor once, and that's going to be sufficient to build a model, because it's going to run this call method. Well, first of all, it's going to call the build method if it's implemented, so yeah, it doesn't do anything. Then it's going to call the plain call method, and in doing so, it's going to call underscore call for all these layers, which for each layer is going to call build, then call the plain call.
Do you recommend users to use things like add loss and add metrics even if they're doing a custom training loop?
Yes, that's totally fine. So using add loss with custom training loops works like this. So after your forward pass, model.losses has been populated. And so you can just add the sum of these losses to your main loss value. For metrics, you're going to have to query model.metrics and look at their names. So for metrics, if you're writing custom chain loop, it's actually easier to do every step manually. So start by instantiating your metrics outside of the loop. Then inside the loop, for each batch, you call update. Then at the end, or like at the end of an epoch, you call results and you log that. Add metric is usable with custom chain loops, but it's not very ergonomic. Add loss is very ergonomic with custom chain loops.
Are all the values in model loss scalars or per batch? Or?
They're all scalars. We don't support non-scalar losses. Correct.
Among all the TensorFlow ops, how many can I access through Keras core layers? And are you still actively developing new core layers to?
What would be an example of?
For example, the sparse ops in TensorFlow.
Yeah.
They're not used by Keras.
So Keras is meant to support a number of sparse operations. For instance, the dense layer is meant to support sparse tensors. I'm not sure if it's true today, but it's definitely supposed to work. Other layers, maybe, yeah, I think it's mainly the dense layer, maybe activation as well. But yeah, the large majority of layers like LSTM, Carve, pooling, and so on, they're only for dense data, dense float data.